If I lose my cursor. Oh, here.
Everybody, welcome to this month and the first of this year's AI for Science Seminar Series. And today we have the pleasure of introducing Tristan Bereau. He's a professor of physics in the University of Heidelberg. I just briefly mention his academic path. He did his PhD at Carnegie Mellon University in the States in physics. And then he moved on to do a postdoc in Basel. And then he was appointed as junior group leader at the Max Planck Institute in Mainz, beautiful Mainz, with an Ingenieur Fellowship, prestigious German award. And then he moved on to for a position in Amsterdam, I believe, for a couple of years. And then he had a quick stint in industry before taking on the position as a professor in Heidelberg. So we are very happy to welcome you here. Thank you for taking the time, and we're looking forward to the presentation. Welcome.
All right, thanks so much. So I hope the microphone's working. I'll step here. Thank you, Rocio and Simon, for the invitation. I've had a great day so far talking to some of you, learning about what you're doing. And I'll tell you a bit about trying to work a little bit visiting calculations of free energy calculations with generative machine learning. And so I'll tell you about this. And in case you're not very familiar with free energy calculations, I'll give you a little bit of background as to what they are. And so if you know StatMech, the first part will be a little bit pedestrian, but I hope I keep everyone on pace. And so to motivate things, I was thinking about something like a protein, for instance, then let's say you're interested in solvating it, and this might be, this might be a computer simulation, in which case you have if I see my cursor here, you may have a periodic box, and then you want to fill it up with water. This might be experimentally, you might have a test tube, and then you want to solvate your protein. And so the question is, of course, microscopically you have water molecules, and the question is how many molecules do you add? Of course, you're interested in the equilibrium condition. And so one thing that thermodynamics tells you is that if you're looking for equilibrium, then you want to minimize this quantity, which is called the free energy. And the free energy scales with the number of molecules that's in your system. And so that's this the n here. So n is the number of molecules or particles. And so you want to minimize the free energy if you want a stable equilibrium configuration. And that with this simple relation here that immediately tells you that this scaling prefactor mu here cannot be constant, because otherwise the equilibrium answer would be trivial. It would either be 0 or infinity. And of course, in your test tube, there's not an infinite number of water molecules or 0 water molecule. There's something somewhere in between. You have a macroscopic number of water molecules. And the reason why that is because there's this term here, which is called the chemical potential, varies. And this chemical potential is something that you can intuitively think about, because free energy is like an energy, but it's called a free energy because basically it also takes into account entropic configuration. So what types of, how many microstates you have, and the configurational diversity. I'll come back to this. And you can see that here you can sort of isolate mu here, and then you'd have this derivative df dn. And so this mu here is the cost per molecule or per particle that you add into your system, right? And so if I add a new water molecule into my system, what's the cost associated with this? And this may be positive or negative. Negative being I actually, I lower my free energy, so I gain free energy, right? And of course, this, like, to some extent, this will do this in the sense that they have very few particles, have a gas, and if I add one more molecule, then there are attractive interactions, and this will make it more favorable, and so this sort of will welcome this molecule in my system, and this is something you can relate to the microscopic interactions, in that there are attractive interactions between atoms. That's coming from the underlying electrostatics of the system. But of course, so this will lead to incentivizing or favoring more molecules to be added together. But at some point, of course, this cannot go on forever, because at some point you have a dense liquid, you pack too many molecules, and at some point there's no more space to put in a new molecule. And so this is where you start having sort of an unfavorable contribution at a higher density. And so this is where, coming from really the Pauli exclusion principle here. And so this quantity here, this cost of introducing a new particle will depend on, of course, the average environment, how many molecules you have, whether it's going to be favorable or unfavorable. And so there is an optimal number, and so it's been one of the objectives in the old literature of computational physics to calculate this, how to calculate a chemical potential, this energetic cost of adding new molecules. And in a couple seconds, I'll show you how this is typically done, the main conceptual idea. Before I do this, I want to sort of bring down the point that we're thinking about thermodynamic properties, where we have a liquid and there's a temperature that's provided by the environment, and so when we think about stability, we have to revise a bit or adapt a bit how we think about measuring stability. So if you're thinking about electronic properties, you may be familiar with quantum chemistry. If you have two molecules or the same molecule in two different configurations, and you're saying which one is the more stable, then this is a statement about their energetic difference, right? So you compute or you measure the energy of one configuration, the other one, and you subtract them, and this gives you the relative stability. We cannot do this in a liquid. That's because any sort of single configurations is not statistically relevant. And you can convince you of this in that if you take a sort of a beak of water and then you drop a droplet of oil, then this droplet of oil does not stay there. It sort of disperses into the water and you don't see it anymore, or it diffuses and it becomes homogeneous. And so it tells you that there's a large number of microscopic configurations that will sort of get that that the system can explore. If you want to make a statement about energetic stability, you have to integrate over all these possible configurations. And it just so happens that your typically system ends up in here because there's just more combinatorics of observing this than there are observing this droplet here staying as one point. And so we're going to have to take some sort of a configurational integral, configurational average. We're going to have to average over all something about stability of our thermodynamic systems. Okay. So all microstates are not created equal. They have different energies, and this is sort of drawn in this cartoon here, in this sort of idea of an energy landscape, in that some microstates have a high energy and others have a low energy. And so when you're integrating this formula to get this ensemble average here, you weigh each microscopic configuration by a weight, that's the probability density, and then this density is the Boltzmann distribution, which is what it's given to you by statistical mechanics. And so this is the exponential of your energy function here. And so this is going to weigh the different microstates, and then you integrate all of them or sum them all up, and then you get your experimental or your observable, which you can then relate to experiments. Okay, and so what it tells you is that this integral is going to be relevant if you don't take into account this observable. Really, you're thinking about integrating over all the possible microstates. This gives you the partition function, which you may in other fields call the evidence or the normalization. But so this tells you that this integral over all the states is going to be relevant. It's going to be an object that's going to be useful to compute. And statistical mechanics also tells you that the free energy actually is the log of this partition function, and so really you can think of it as the log of a phase space volume. And so when we're talking about free energy, we're talking about the number of microstates and the volume in phase space of all these microstates. And so computational physics has sort of a long history of trying to compute this, and these are difficult. And as you can imagine, we're going to take a possibly high-dimensional integral and have to evaluate this very accurately, and then take the log in order to say something about the free energy, which then allows us to say something about relative stability. So this is something that people do in, say, drug discovery, right? If you're trying to, say, optimize for a small molecule that would inhibit, say, the function of a protein, you want it to bind strongly to it, maybe. And so you would compare two molecules, and then this relative stability would be something that's very relevant to compute. And so again, this free energy difference would be a log of the ratio of partition functions, which is something that would look like this. And of course, these would be high dimensional, and so this looks ugly and is difficult to compute practically. The way that's often been done traditionally in computational physics is to try to look for sort of configurational overlaps between your two different distributions here, and then use this to build an estimator of this free energy difference. And of course, that tells you immediately that the degree of success of doing this will depend on how much overlap there is. If there's very little, it's going to be difficult because you have an exponential distribution, you may only have an exponentially small overlap between your tails. And back to our calculation of the chemical potential, a similar idea happens in that the way this is typically done is that, very sort of simple cartoon, you take a system, you have a number of molecules, maybe water molecules, and then you try to add a new one. So this green one here. And the chemical potential is, if you take this sort of a numerical approximation for the derivative dfdn that you see there, you can write this as an approximation to the free energy of the system with n+1 particle minus the free energy with the n particle system, and this is something that can be written out in this way, and that you have again this configurational integral where you evaluate this particular integrand there. Now, what's relevant about this part here is that actually I think the bracket should not be there. I'm sorry. What's relevant here is that this is a perturbative method in that we're taking an integral of the n+1 system, so this system here, but we're evaluated in the ensemble that's generated by the n particle system, and so in that ensemble there. And so I'm taking the probability density of the n particle system, and I'm evaluating what would be the effect of adding this new particle. And in this sense, it's perturbative because I'm sort of assuming that these two distributions are very similar. Yeah, of course.
How do you evaluate this? I mean, you have your sort of your average. So the bracket here is over n degrees of freedom, right? And you have an integral over n+1 degrees of freedom. How do you do this in practice?
Yeah, so this would go into the delta U here, and that you would compute the impact on the energy, so the change in Hamiltonian between this configuration and that configuration in the absence or presence of this new particle, but only taking samples from the ensemble of the n particle system. So in this sense, it's perturbative. You're not taking into account the ensemble of the n+1 particle system. Okay, and so in general, so this was sort of a little bit of a motivation to thinking about whether these old ideas from computational physics can be revisited a little bit by generative machine learning, and in particular these free energy calculations. And so I want to talk a little bit about how generative machine learning has, in the last few years, tried to revisit free energy. So I'm going to talk about what people have done in this area. In this sense, I don't want to talk about, say, let's say the straightforward problem of a regression problem of, say, if I give you free energy labels, I can fit, I can use I can write a supervised machine learning problem and then do a fitting of these free energy labels. That's not what I'm going to talk about. I want to think about, in more detail, exploiting the underlying statistical mechanics of what a free energy means, and then trying to relate this to architecture that's provided by generative machine learning. And if that sounds a bit abstract, I'm going to be a bit more concrete in the next few slides. So this idea so one of the first ideas was to revisit this idea of free energy perturbation. So I just talked about a perturbative method for the calculation of the chemical potential. Actually, this is an old idea that's coming from Swansig, which says that you can compute a free energy difference, and a good estimator could be that you do this calculation, which is you look at the free energy or the energy difference, and then you evaluate it in the ensemble of A, where you'd have state or ensemble A here and ensemble B, and you're trying to compute the free energy difference between A and B, and you do this by an ensemble average that's only sampled in A, not in B. And again, you can imagine that there are these issues of configurational overlap, in that if A and B do not overlap well, then this will be very difficult to sort of reach out and sort of pick points from B and evaluate the difference here, only evaluate in the distribution of A. And so one way to do this is to say, well, okay, let's write intermediate distributions and work these and sort of do this in a pairwise manner. So now, if I take this first sort of this first circle here, I can do this freely difference between these two, and then I can do it in a pairwise manner. And so that's been sort of something that's still heavily used in, say, in alchemical transformations. If you do molecular discovery, for instance, you write a lot of interpolating Hamiltonians. Yes, and so this is something I talked about in this particle insertion method. Another idea that was proposed by Jardinsky about 20 years ago was to say, well, what you could do is take the distribution of A, and what we really need is a high overlap with B. And so nobody prevents me from trying to find a transformation that takes me from A to a distribution A prime, which does maximize or has a large overlap, configurational overlap with B. And if there is high overlap between A prime and B, then now this perturbative method will work really well. And so this is a great idea, but of course, nobody tells you how to do this transformation from A to A prime. There are ideas from the statistics literature in what's this called? I think of warp bridges, for instance, I think, which basically means you try to link these two distributions through the moments. For the different moments. But of course, if you have a 100-dimensional distribution, working in moments is not going to get you very far. So this is actually a very hard thing to do. And then about 20 years later, then there was a paper by Welsberger and others from DeepMind that said, well, we don't have to know this mapping, we can just learn it. And so we can learn it with normalizing flows. And this is something that then they applied to a number of systems, like Lennard-Jones clusters and such, and was working really well. And so you can sort of use normalizing flows to learn this transformation from A to A prime, which maximizes the overlap with B. And then you can use that formula. And that's called targeted free energy perturbation. Another approach, of course, was the Boltzmann generator, worked out with Simon and others, which really are normalizing flows, or I'm really simplifying, normalizing flows with an energy-based model, where you're trying to convert or transform a trivial Gaussian distribution into your data distribution by applying a number of transformations to then really sort of implement your Jacobian. And there's two ways that free energy calculations were made in that paper, if I understand correctly. One was sort of a relatively straightforward in that you could sample your latent space, transform back into your data distribution, and then sort of simply count on which side you're on, and then sort of measure the size of your distribution and your data distribution here, and this would give you a free energy difference. The more interesting aspect, which I think was really new, is that they showed that you could train two Boltzmann generators on two distinct parts of your conformational space. Think about protein that's folded, one that's unfolded, and you may not have configurations that allow you to connect these two. But if you have two distinct basins and you can train two individual models, you can then relate the free energy difference, which is something that if to the best of my knowledge, something that computational physics has always failed to do. So we've always required sort of connecting states in between. Yeah, right. Yeah. But yeah, that worked really well. Okay, so I'll tell you how we've tried to do it. Before I tell you how we do it, I'll tell you about the systems we've worked on first. I'll talk about a few systems. We're going to build up towards more chemical systems toward the end, but I'll start with very simple Lennard-Jones particles. And so this is actually the same potential, interatomic potential I showed you at the beginning. So it's one of the simplest interatomic pairwise potentials as a simple model for, at least for noble gases and lots of molecules. It's used a lot in atomistic force fields, for instance, to describe how atoms interact. And so we're going to use, so we want to generate configurations of Lennard-Jones fluids. So these look like this. And so this would be there would be periodic conditions, right? And periodic boundary conditions. And we've used grand canonical Monte Carlo simulations to generate training data according to this interatomic potential. Yes. what we're going to do in the end, I'll show you, is that we want to train a single diffusion model for different particle densities. I'll come back to this. So what we'll use to do free energy calculations is something called thermodynamic integration, which is a slightly different method to compute free energies. It is not perturbative; it's exact, and it relies on the idea that a free energy difference, which means that it only depends on the endpoints, so it does not depend on the path you take. And so that means that if I'm interpolating between two Hamiltonians, right? I have two systems. I have a molecule, another one, or a molecule in an environment with a molecule in a different environment, for instance. So I have two Hamiltonians, and I want to compute the free energy difference between these two Hamiltonians. I'm free to choose whichever path I want to take to connect the two. And so I'm going to dream up a coupling variable, lambda, and this will describe the path that takes me from one Hamiltonian to the other one. And so, and if I do this, then I can rewrite my free energy difference as difference in log partition functions. And so I can rewrite this as this integral over this coupling variable by taking the derivative of the log partition function with respect to that coupling variable. And again, because this is a Tate function, then this is exact. Now, if you plug in the Boltzmann distribution for this, then what you get with simple algebra is you get this expression here, which is that the free energy difference is the integral over the coupling variable, so this path that we're taking, of this particular ensemble average here, which is the derivative of my energy function with respect to the coupling variable sampled at the particular value of that coupling variable, right? So I'm walking along my coupling variable, and at any point, I have an energy function which describes sort of an interpolating Hamiltonian between the two, and I need to sample this, and I calculate this derivative of the energy with respect to lambda. Okay, this is how it's done in also for this is called alchemical transformations for molecules. It's done heavily also in computational chemistry and drug discovery, and you also have the same problem that, of course, typically you have your two endpoints are far apart, and so you typically have to compute this for different interpolating Hamiltonians between the two in order to sort of have a good discretization of your integral here. So you need sufficiently many points in between. And so that requires on many simulations of intermediates in between, which are not quite this molecule but not yet quite that molecule. And so that's called alchemical because it's not physical or not chemical. They're sort of in between. Note that this is true for any energy-based model, and so this is actually not sort of related. This is not strictly sort of limited to equilibrium statistical mechanics. Whenever you can write your probability density as an energy-based model, this will be correct. And so, in fact, this has been used outside of physics. For instance, in this paper where they used it to tighten the elbow in variational autoencoders. And sort of being able to write your distribution as an energy-based model, that means that you can write it as a log of something, and so that sort of, as long as you don't have a pathological distribution, this is something that's quite general. Okay, but here we're using physics, so and so we're going to make use of this, and note that something interesting shows up in that here. So if I want to compute a free energy, then I have to calculate this integral, and then the energy function shows up. And of course, what's interesting is that if I have a generated model, and say I use it to generate structures, like so I want to generate these like Lennard-Jones configurations, then what really it means that under the hood it's learning an energy function, and so it needs to learn this energy function in order to generate samples that correspond to these particle configurations. And so we're going to sort of do we're going to use twice the same energy function, one for the structure generation, and then we'll use it to compute these free energies. And so we're getting the free energy sort of for free, in that we train the model just to do structure generation, and then we'll use this equation to compute free energies. But our training has never seen any free energies, right? Okay, and so we're going to use diffusion models. Change of architecture later, but for now we started with diffusion models. we work with, so we start from data distribution, and then you sequentially corrupt or noise your data by adding a Gaussian kernel. In a Markov process, if you have a discrete diffusion model, we're using a continuous time formulation, which allows us to write a stochastic differential equation that looks like this. And the beauty of diffusion models is that you can write in closed form the time reverse stochastic differential equation. And when you do that, the thing that shows up is this object here, which is new compared to the forward path. And this object is typically called the score. And so that's the spatial gradient of the log of the probability density at time t. And so really training a diffusion model means learning the score here. And this allows us to denoise, to work out a sample from our data, from a latent space. Okay, so the way we train more specifically is using something called denoising score matching. Denoising score matching means that so the problem with score matching is that it requires you to, of course, you want your model to reproduce the score, and this would be the true score. And the problem is that the true score typically is not known, so you typically don't have access to the true score of your model. But what you can do is a trick that is proposed in this paper by Vincent here, which is you could say, which is so-called denoising score matching, which says you can take a sample and then noise it and impose a certain noise schedule, for instance, Gaussian noise. And what he showed is that you can write this denoising score matching loss, which is now this conditional distribution of this noisy data that's conditional on the noiseless data here. And so basically what you're doing is that you noise your data, and what you're trying to learn is how to correct for the noise that you've introduced. And in particular, if you say this noise is Gaussian, then this object here corresponds to a restoring force that you're trying to cancel or to correct for. And so this is something you can easily construct and then learn against. And so that's the idea we'll be following here. Okay, so the score then is this spatial gradient of the log probability density. And so again, we're going to use an energy-based model because we have a Boltzmann distribution. And so if I take my Boltzmann distribution and I compute this gradient log, then I have simply the gradient of my energy function that stays here. And so what we'll do is, instead of learning the score as a neural network, we'll have it learn this energy function directly. And the reason we do this is because, first of all, we know that we have a Boltzmann distribution at the endpoints, and so we know that this has to have this particular form. And the second thing that's interesting is that actually this energy function is, as I said, exactly what we plug in here in the free energy calculation from dynamic integration. And you see that I've replaced the variable lambda, the path. I've replaced lambda with t, which is time, because I'm going to associate this coupling variable with diffusion time. And so what I'll say is that I'm going to have a diffusion model, and this pathway of interpolating between two Hamiltonians will consist of sort of denoising my diffusion model, right? And lambda with time here. And so this integrand is the time derivative of my energy function. Okay, and so we're not even going to do this. So this score, actually, we're going to apply even more sort of boundary conditions because we know a few things about it. So we'll add even more physics in that the traditional way from computational physics, the way that these calculations are typically done is by using a so-called soft core Lennard-Jones potential, in that you sort of smoothly turn it off and you make it go to zero. You have to turn it off and smoothly because otherwise you have divergences at zero. And so if you look at this score, and then so if you forget about this first term here, but you only look at that term here, this is exactly what you do in sort of traditional computational physics of doing from dynamic integration. So you're plugging in this soft core dependent Lennard-Jones interaction, and then this is what's used to then compute these free energies. And so what we're doing is we're going to use this, but then we'll only have that new part as a neural network. And so we're going to learn a correction on this sort of classical way of calculating these free energies. There are factors of t and 1 minus t in there, in that we interpolate, so time goes from 0 to 1 in our model. And so you can see that these factors of t and 1 minus t will turn off these terms either at t equals 0, at t equal 1, or at both. So for instance, here, we don't want the neural network to contribute anything at the endpoints. We only want it to inform something along the way. Yes. And at t equals 0 here, we want this to be the fully interacting Lennard-Jones potential, so we want this to be fully on. Yes. Another aspect that we'll exploit is that we're going to associate sort of physical meaning to our latent space. And our latent space is going to be the space of non-interacting particles. So we have in our data distribution, we have our Lennard-Jones particles. So they interact through the Lennard-Jones potential. And so as we noise, so we go to the latent space, then we still have our particles, but then they don't interact anymore. And so what that means, mechanics is called an ideal gas, in that they would have kinetic energy and that they would move, but then they don't interact. And so this is something that's great because we can write out analytically what the partition functions and the free energies are for this system, because that's a trivial system. And what it also tells you is that sort of interpolating between the latent space and the data distribution corresponds physically to coupling the interactions. So my free energy now has a physical meaning. Okay, and then the last part of physics we'll put in is that we work with periodic boundary conditions. So actually we're, unlike many other works on diffusion models, we're not going to use a Gaussian distribution in our latent space, because that would change the topology, right? We go from a finite support to an infinite support. Instead, we're going to work on a torus, which means we have a multi-dimensional sort of a uniform distribution in our latent space. And that keeps the same topology between the latent space and the data distribution. And so learning that data transformation is going to be a lot easier. Okay, so this is how it looks like. So now on the left here, I have the interacting system. And then on the right, I have the ideal gas, so the latent space. These particles have different colors, that in blue, they would be sort of separated enough that they don't, so they satisfy this repulsion, so this Pauli exclusion principle, whereas in red, there would be significant overlap. So there would be so-called steric clashes. So I can show you a movie here where we start from the latent space and we denoise, and you can see how these particles slowly turn blue. And at the end, they're all blue, and that they all sort of satisfy these steric constraints. And so this is after training of our model. The question is like whether this type of configurations that we get are meaningful. So we can check for the structural accuracy. There's different ways to do this, but one simple way is to look at the pairwise statistics of how these configurations, what type of configurations they sample. And that's called the radial distribution function, this G of R here. And we can do this at different particle densities. So the row here, I apologize, this is not the probability density, this is the particle density. So this is the number of particles divided by the volume of my box. And so at low values here, this is like a gas, and at high values, this is like a liquid. And so with the same model, you can see that there's good agreement between red and gray, which one is our diffusion model, the other one are the reference Monte Carlo simulations. So you can see that at some point it crosses a phase transition and seems to be doing well overall. But what we're really interested in was to see how accurate these free energies are. And so we can actually, once we have trained our model to compute these, to generate structures, we have an energy function. We can plug that into this thermodynamic integration formula. And so that's the result here in this plot here of this delta F as a function of this particle density. So again, here to the left, it's like a gas. There's very few particles in my box. And then toward the right, this is a very dense liquid. There's lots of particles. So the curve is in black from the diffusion model, and then in the colored curves, these are from classical thermodynamic integration with different numbers of intermediates that we use. And so you can see that first we need between 50 or 100 intermediates to get close to what we get with the diffusion model, which only requires knowledge about one endpoint. There's a bit of a discrepancy between the two, probably coming from both from our convergence of the Monte Carlo calculations, but also maybe some limited expressivity of our machine learning model. But you can see that this is very good. Actually, another way to check that this is accurate is actually to also go back to this chemical potential, which I introduced at the beginning. So this cost of adding a particle, there's a trick that allows you in statistical mechanics called the equivalence of statistical ensembles that allows us to compute this from these free energies that we have. I'll skip the details, but basically the results are shown here. So these are the red curve is our results, and then there are sort of reference calculations in black. And you can see this is also very, very accurate. And so that's the cost of adding these particles. And so that works very well. It gives us accurate results. What we get from this is we only need data from one endpoint instead of having to sample molecular dynamics or Monte Carlo simulations at lots of intermediates. Of course, one thing that we cannot do at this stage is we're sort of limited because because of the diffusion model, we have to go from a trivial distribution to our data distribution, our particle configurations, which is not exactly what's the most relevant in terms of chemical applications. So one sort of chemical application is our so-called solvation, which would be, for instance, like this, where I would like to know what's the impact of inserting a molecule inside a particular liquid, right? So if I insert it in water, if I insert it in some oil, what's the impact, the energetic impact? And you can tell that from our architecture it's not going to work because we need to be able to insert our molecule here into an existing environment. And so we are not going to tackle this, we're not going to work with diffusion models. We'll work with something that actually is very closely related, but you could even argue is a bit of a generalization, or stochastic interpolants, or general flow matching models that allows you to connect two non-trivial densities, like here, this rho 0 and rho 1. And then what we'll do is we're going to parametrize, we're going to have to parametrize how we relate the samples in between our two distributions at time 0 and 1. And then we're going to do, again, denoising score matching based on this. And so the idea is going to be similar, but we're not going to do diffusion. We're not going to use the diffusion model so that we can have two non-trivial distributions now. So this is an example of doing it again in a Lennard-Jones system where we have one sort of larger Lennard-Jones bead. It's also the same interactions, but with I think larger radius and larger energetics. And you can see here that we go from, so this particle is always there, but here its interaction with the environment is turned off here. That's why we don't show it. And then we slowly turn it on all the way until it's fully coupled there. And so we want to know what's the free energy difference of sort of like coupling this orange particle in. So actually the movie here should show you, yes, so particles are slowly moving, and you can see that the orange particle is slowly being turned on here, right? And of course, if you pay attention to the particles around it, they have to make space in order for the orange particles to show up. And so this is a comparison of this free energy difference of solvation. The orange one is the traditional method, and then in blue here we have with our neural network here. And you can see that one thing that we can also look at is how we have to soften the interactions. This is like looking at the different interactions between these different particles. And what it shows, what this particular thing, yes, this one is showing you that the softening of the solvent-solvent interactions to accommodate for the fact that there's like this orange particle that you're tuning in. And so there's something that we learn and that is not sort of parameterized in, that allows to, that is learned during the training process. The other aspects to go a little bit more into chemistry, and so of course we like to work with molecules, and so the big difference between what I've shown you so far in molecules, that there are intramolecular interactions, and so here I'm showing you results for water and methane that we solvate in water. So here this is this water molecule in a liquid of water, and then here this is a methane molecule again in water. And so we again want to do the same experiment of inserting this, or coupling this one molecule into water. And of course, the main difference is that we have intramolecular interactions. So the way we do this is, well, there's two differences actually. One is these intramolecular interactions. So we describe all molecules as rigid bodies, rigid molecules. And so this increases our interpolation space to also the space of all rotations of all different molecules now, because they're not isotropic anymore. And then the other aspect is that we are you can see here, actually, we start from atomistic force fields. And the one thing we're missing from atomistic force fields for the non-bonded interactions is that there's two parts. One is van der Waals, which is the Lennard-Jones potential. So this is fine, we had them. But there's also electrostatics. And so we had to add Coulomb interactions to describe the coupling of the electrostatic interactions. And so that's what we implemented. And you can see here on the right movies of turning in the interactions for the two solids. So here the water and here the methane. They're slowly being turned on. And you can see the water molecules around sort of making space for them. You can see here that we get very accurate results, and that the blue and the orange bands here, the horizontal bands, are experimental measurements. And then the different curves are different experiments that we ran with the neural networks. And so they're close. And then the other thing is that we can also, interestingly, we can take the trained model, say this model for methane, and then plugging it to do the calculation for water, and then vice versa, take the model we trained for water and then plug it into calculating methane. And we actually get an accuracy that's actually about 2 kT, so actually not too bad. So there's actually signs of transferability, which probably comes from the transferability of working with the underlying graph neural networks that we have, and then sort of correctly interpolating between the different endpoints that we impose. But sort of this aspect of transferability potentially has interesting potential in sort of scaling up these calculations for more compounds. All right, so I'm at the end, and so told you about this type of thermodynamic integration with neural networks. So in particular, at the beginning, using diffusion models together with energy-based models, which allows us to sort of parametrize the score or write it out really as this derivative of a potential, which we then recycle and use in the calculation of the integrand that we use in thermodynamic integration. And then what happens here is that the diffusion model learns a better alchemical pathway than what you would probably write out yourself if you do it traditionally. I don't think it learns the best pathway. I think there's room to improve this further, and then you can go into optimal transport and things. But it probably learns a better one than if you do it sort of in a traditional way. And then for more sort of chemically relevant applications, we're typically interested in free energy differences between two non-trivial Hamiltonians. And so this is something that can be done with these stochastic interpolants, with flow matching, and then together with adding a little bit of chemistry. And so that really meant adding Coulomb interactions, and then working at least here within this rigid body framework to describe rotations of molecules. And with this, I'd like to close. Thank you very much for your attention.
Thanks a lot. In your last example, the water molecules, they are rigid, is that right?
Yeah.
Is it necessary to use rigid water? I mean, obviously it's easier than using bonds, but that would not be a problem in principle to include the bond interactions, right?
So we tried for a while to include explicit intramolecular interactions. I don't think we have a very good way of doing it at the moment. I think what happens is that your neural network learns an energy function that has many different modes between the non-bonded and the bonded interactions. And the bonded interactions are typically very high frequency modes. And so coupling all of that makes the learning process a lot more difficult. And I think if you think about if you think about force fields, and you sort of like explicitly sort of do this scale separation in terms of modes, like for the bonded and unbonded, we don't really have a very good way of separating this. And I think that's made the learning process a little bit tedious. And so I don't think we have a very good way of doing it at the moment. I don't think it's impossible. I think, you know, I think it will happen. I also think for these examples, it's not critical in that, you know, waters, I mean, for the type of systems we're looking at, this is fine. Of course, if you're interested in something like a little, you know, small peptide or something, then you would get into trouble.
Classic use case of
Right. Then, I mean, but then, you know, you could think about, you could improve on this and then think about introducing, you know, dihedral degrees of freedom, for instance, like the way diffdoc has been doing it, or things like this. Or you could go fully flexible, but then I think it would require a bit more thought.
This is very impressive already. So, of course, what I'm asking, what I want to ask about is basically how far away are we from doing this for protein ligand interactions? But I guess then this would be an order of magnitude harder, but not in principle impossible. That's what you're saying, right?
Yeah, so I think, I mean, if you look at like, so there's two aspects. One is, so if you want to scale up, then there's the force field, and really it's about the intramolecular interactions. Because for the intermolecular interactions, we have basically all of it for atomistic force fields, including proteins. In terms of functional forms, you need to support. And so it's the intramolecular interactions. And then the other aspect is, you know, a sort of a scaling aspect of how many degrees of freedom can your machine learning model handle. So here we had about 500 particles, so maybe 1500 degrees of freedom. If you had a protein, you'd need like a much larger box, and so I can't comment on to, you know, how this would scale.
Like finding in the CV, because you should know what is the CV, like you just define it, and then it's not easy like calculating the only. And can we just use this for any other CV, like a distance or something, like moving like a distance?
I think if you have a distance, then I've never thought about this. How do you do this? So you would have different restraints. Yeah, it might be, yeah. If you would have different restraints, and then you would interpolate between the two systems with different restraints. Yeah, it might be, yeah. I never thought about this. Interesting.
What software did you use to calculate the TI? Like, is it King, Gomax thingy, or?
No, this is all done by Balint, actually. Actually, I should acknowledge Balint. I failed to acknowledge Balint at the beginning. It's like the one thing I had to do. And this is done by Balint. It was a spectacular. He was visiting PhD student from Geneva, and so he coded it all up himself. And so basically all in JAX. This is all done in with Monte Carlo simulations. Yeah.
Transferability, is that because you just have two terms in your interaction, so you just have the Coulomb and the Lennard-Jones, and that's why you see a little bit of transferability even if you don't have the same elements? Is that correct understanding? I'm just trying to understand.
Yeah.
Understand if you have one or methane water, that would be maybe transferable to a water.
Right.
The other way around,
So I don't understand it very well, but like I think it's a mix of, or a combination of, one is a sort of a general transferability of these message passing graph neural networks, in that, you know, let's say the water has never seen methane interactions, but so it'll do a different type of, you know, the message passing and the node updates will be a little bit different, but probably things are sort of constrained. And will get better, of course, as you increase more diversity in your training. I think what also happens here is that, you know, we're constraining the two distributions of our endpoints. and so and this sort of limits sort of how wrong it can go, because it sort of you're I think there's a lot of, let's say there's a lot that you get out of the interpolation between the two endpoints. This is something I'm not able to, that I don't understand very well, but I think there's something to that, and that we sort of, there's a lot of restraints from the nature of the problem of this interpolation, but I not very well explained because I don't understand it very well. But I think it's probably a mix of these two. This would be my best guess.
So in terms of data, this thing is also trained on data, and how does this compare? Sort of like what is the upfront cost that you need for generating data compared to the sort of the gain of like converging a traditional approach?
Right. So roughly in terms of wall time, it's about equivalent at the moment between training a diffusion model or running these like 50 or 100 intermediate molecular simulations. And so at the moment, it's let's say it's competitive. I think there are more prospects through these types of transferability later on, and then there might be also optimization you could do.
So if you learn the
Yeah.
path,
Right. I think so. Yeah. I think so. Yeah. That's right. Yes. I think that has a big impact, right? I mean, like people have tried for a long time to find heuristics or find sort of better understand what would be good paths and whether you could write this down sort of before you do any calculation, right? Like how do you interpolate between your Hamiltonians? What type of coupling you do? And there are works that like try to better understand this, but it's still not. I think there's still room to improve on this.
Certain this methane molecule, for example, in the water. How do those intermediate steps look like from a phase space picture? You don't really have the whole molecule, but you have something.
All right. Yeah. So this is okay. This is where you would typically write these sort of like interpolating Hamiltonians between your two sort of physically meaningful systems, and then what the fact that you can't take any pathway, that means you are allowed to sort of interpolate however you want, and so you can write any sort of and often not of it. So you think about like you have two Hamiltonians and you interpolate between them, and so you're like maybe t times one and 1 minus t times the other. It could be more complex, but this will work, for instance. And this is often how it's done. And so it's sort of really a mix between two Hamiltonians, which physically doesn't make any sense. Yeah, or yes. I think one way of, you can also like, if you look here like this would mean like you would scale down your interactions, for instance. You'd scale down certain interactions, scale up others, right? Which, I mean, if you don't get to scale them down. I mean, maybe you increase temperature, then things move, but really you can't like just scale interactions down. The torus. Oh yeah. It's because so models they describe their latent space with a Gaussian distribution, right? But so here when when we denoise, so we denoise like particle configurations that are in a box, right? And so along a coordinate here, this is only defined between say 0 and 1, right? Spatially. And then like if my particle moves beyond 1, it comes back at 0. right? And so there's absolutely no density outside of the 0, 1 interval. And so so this has like finite support, right? Because there's absolutely no density outside. And if I'm now I'm now trying to like find a transformation to a Gaussian which has infinite support, it just makes it a bit awkward, right, topologically. This is a this is a torus, yeah, that's right. This is a torus, yeah.
It's really anything, right?
Yeah.
So you could choose it in a way that also all intermediate states are physically meaningful, right? For example, if it's a function of temperature or something else. But so I think if I understand correctly, the problem with that might be that we cannot find a generative model where you can take the time variable of that model to match this interpolation variable, right?
What do you mean by this?
You have like two time variables. One of them is the interpolation variable lambda, right? And then you have the time variable of the dynamic model.
Oh, yeah, right. Sure. Yes.
And you can choose lambda to be physically meaningful. And this would principally be nice because then you can also like calculate differences between all the intermediate states, if you like, right? But I think the trick was that you found a model that the T has the same meaning as the lambda. That you were saying that I think it's difficult to do that for a physically meaningful variable, right?
Yes. So, well, okay. Okay, one comment is that I never talk about like sort of simulation time or real time, and that this is all like equilibrium data. And so I don't, you'd have to think hard to adapt this to say kinetic quantities, right? Where you actually need like simulation time information. So here, this is all equilibrium, so I just need ensemble data. Yeah. Okay, yeah, this we associate with this lambda couple. Yeah, this lambda, yeah.
Like for example, the temperature. Can we also find a general model that like matches this variable?
So I'm not sure if I'm not sure if I can answer this well. I think here this works because the lambda we're free to pick any lambda. And so I can think about, yeah, so if you want to work with temperature, for instance, in a process where the choice of temperature doesn't matter, then you're free to pick whatever you want, and then so you could associate it with it. But chances are you do need to think about that, and so this might, in general, probably won't work. Yeah, so you would need to have we can only make this relation between lambda and diffusion time because lambda has no meaning.
Yes, if it has a meaning, it's probably in most cases not possible.
Right. That could well be. Yes.
Question online from Wanky. He said Markno network architecture was used, and the other questions I believe have been asked.
Yeah, so it's a graph neural network, and it's a Schneid model, and it's a Schneid model that actually is sort of supplemented with a little bit of directional information. And so it's not a vanilla. So Schneid models are very common to describe atomic potentials, and they use radial basis function kernels. And here this is sort of augmented by these sort of simple vectorial information. I think then yes, I'll leave it at that. I think so. This is what we used. I think there's ways to improve on this, and I think Valentine might even improve on it, but I don't remember at the moment.
Data, I believe, has been answered already, and also transferability we also discussed already. So, no further questions. I think we can thank Tristan again.
All right, thank you.